Hello, I'm Hilairy Hartnett, and I'm delighted to be here today at Virtual Goldschmidt. I really appreciate the opportunity to speak in this session, and today I'm going to tell you about exoplanetary ecosystems, what we know about them, and what we need to know about them. I'm a member of the ASU Nexus team, and I owe them a great deal of thanks for helping me to frame these ideas. So the first take-home message for this talk is that we know almost nothing about phosphorus in stars and in exoplanets. Yes, other elements are important, but a key message is that phosphorus is really poorly known. Second take-home message is that if we can detect water on an exoplanet, it's probably too much water, and that life detection on those planets might be extremely difficult, which is counterintuitive. As Natalie showed us, planets are common and diverse, and we can imagine that there are many, many planets that might be similar to Earth. The traditional habitable zone is based on liquid water, but I'm going to put it to you that detecting life on those planets is more than just the presence of liquid water. We need to understand the rates of chemical and biological processes on those planets, and that detecting life is going to depend on the rates of those processes. So the chemistry of exoplanets is rather poorly known at this stage, so we assume that planets will look like their stars. Fortunately, we know a good deal about the elemental composition of stars. This is data from the Hypatia catalog. Hypatia is the largest catalog of elemental abundances for nearby stars. The bar chart has elemental abundance, elements on the x-axis, about 73 of them, and the height of the bar is the number of stars with a measured abundance. So for example, these rock-forming elements, magnesium, silicon, calcium, there's about 5,000 stars in the catalog that have data for these elements. For bioessential elements, some elements there's a good deal of data. There's 4,000 or so stars with carbon data, 1,500 with nitrogen data, and only 92 with data for phosphorus abundances. So the ratios of elements are critical for life and for geology. I'm an oceanographer, so I'm going to use plankton as my proxy for all life. And canonically, plankton have a carbon, nitrogen, phosphorus molar ratio of 106 to 16 to 1. And that's based on the equation for photosynthesis, which I put here at the bottom, that assumes that phosphate, or phosphorus, is the limiting nutrient for this reaction. We can look at the composition of the Earth's crust in a similar way, and we see that the C to N to P ratio for Earth's crust is much more nitrogen deficient. For comparison, I looked at the bulk silicate Mars model, and it might not be a direct analogy to the Earth's crust, but we can see that Mars has much lower carbon and nitrogen relative to phosphorus than the Earth, although presumably habitability on Mars is a bigger problem than just having enough phosphorus. Similarly for stars, our sun has a C to N to P ratio that's much more carbon rich, 2,000 carbons for every 550 nitrogens for every phosphorus. But our sun may also be different from nearby stars. The average star in the Hypatia catalog has a much lower amount of carbon and nitrogen relative to phosphorus than our sun. Let's look at the data. This is the Hypatia data for nitrogen, carbon, and silicon presented as molar ratios. Carbon to silicon ratio on the x-axis, nitrogen silicon ratio on the y-axis. The circles are the stars, about 1,500 of them. The ones that are black are stars with known exoplanets. Presumably many of the stars that are green also have exoplanets, but we haven't detected them yet. And this is plotted in a way that's not familiar to most astronomers because they use a solar normalized frame of reference. These molar ratios show us that our sun is somewhat outside of the bulk of the planets in the Hypatia catalog. Plankton are down here with less carbon and less nitrogen than the stars, and the Earth and Mars are very close to the origin. The ratios are small because these planets actually have a lot of silicon, which makes sense. They're rocky. planets. But I started out talking about phosphorus. As soon as we attempt this analysis for phosphorus, we find out there are very few stars, only 51, that have abundance data for nitrogen, phosphorus, and carbon. So now this plot, which is carbon to nitrogen ratio on the x-axis and carbon to phosphorus ratio on the y-axis, shows us that our sun may be relatively normal in terms of carbon and nitrogen, but it's definitely carbon rich or phosphorus poor compared to the few other stars for which there's data. Ultimately, we don't know very much about phosphorus composition of exoplanets because we don't know much about phosphorus in stars. And so I think there's a real need for getting more phosphorus data from stars that have exoplanets, if we're going to think about how to make models of planets that are based on the elemental compositions of those planets. We shouldn't really be inhibited by the lack of data. We can look to the Earth systems and we can build models for exoplanets based on those kinds of systems. Excuse me. A systems perspective is key. This session started with a nod to Darwin and the warm little ponds, which might not be quite right for the origin of life. But Darwin was a profound thinker. He's reputed to have taken Charles Lyell, here on the left, his treatise on the principles of geology with him on the voyage of the Beagle. And indeed, Darwin's writing and publications are illustrated with beautiful geologic maps and sketches. He knew that living systems responded to their environments. And I think this approach of thinking about the geochemical and geological system in which an exoplanet ecosystem evolves is going to be important. Here's an analogy. This is a Winogradsky column. We use these in classrooms and demonstrations to discuss how there are many metabolisms present in one system. So this is built out of a 2-liter bottle. You can imagine it has a lid. There's algae in the top, and there's many different kinds of bacteria with different metabolisms in the sediment. If you measure the amount of oxygen in the headspace, it integrates all the metabolisms that produce oxygen and consume oxygen, and presumably any non-biological processes as well. So you can imagine for an exoplanet, the atmosphere is like measuring this integrated signal of all the processes at work at the surface and below the surface of that planet. For exoplanets, it's not going to be enough to say that a biosignature gas like oxygen could plausibly be produced by life. We also have to demonstrate that it is implausible for that oxygen signal to be produced abiotically. The ASU Nexus team has developed the Detectability Index as an effort to quantify these two things. It generates a range of values rather than the yes-no answer to detectability, which is nice. And it is essentially the biological source of a biosignature gas like oxygen relative to the non-biological sources. It depends on having reasonable models of both biological processes and geochemical processes. And positive numbers and large positive numbers indicate a greater likelihood that the gas is produced by biological sources than by non-biological sources. Let's walk through this calculation for the Earth and for water worlds that have more water than the Earth. This is a cartoon of the oxygen cycle on the Earth with both biological processes like photosynthesis and respiration, and non-biological processes like photolysis of water in the atmosphere due to UV light or consumption of oxygen by reduced gases. On the present day Earth, we produce oxygen to the tune of about 10 to the 4th teramoles per year, and we consume oxygen also biologically through respiration, approximately 10 to the 4th teramoles per year. So there's a net flux of oxygen to the atmosphere of 20 teramoles. This is much, much larger than the production of oxygen in the atmosphere due to photolysis of water. If you calculate the detectability of index for oxygen on Earth, that 20 teramoles divided by 0.02 teramoles yields a detectability index of 3. But what happens if you have a planet that is perfectly habitable, could be a water planet with a lot more water than Earth. It only takes about 5 oceans of water to submerge the continents on land. From the standpoint of a planet's water content, that's still pretty low. But now, our continents are below the surface of the ocean and there's no weathering. This is a problem for supplying phosphorus to this ocean. And the reason for that is that phosphorus is a rock-derived element. This is a picture of apatite in its gem quality form. It's a beautiful blue color, and it has a large amount of phosphorus on a molar basis. It's a highly insoluble, generally speaking, an accessory mineral, so it's not highly abundant. And its solubility product, the log of its solubility product is something on the order of -40, maybe as small as -100. It doesn't dissolve very easily. Yes, surface complexation reactions can help it to dissolve better, but it's still going to be extremely insoluble. And on today's Earth, the phosphorus supply is about 0.07 teramoles per year. We calculate for our pelagic planet with 5 oceans of water that the phosphorus supply is going to be 2 to 3 orders of magnitude lower. Well, less phosphorus means less photosynthesis. So now on this pelagic planet with submerged continents, there's much less photosynthesis and respiration, and we estimate about 0.02 teramoles of oxygen delivered to the atmosphere each year by biology. Now, biological production rate is of the same order as the non-biological production rate. This planet might still be habitable, but the oxygen flux to the atmosphere is much smaller, and it's difficult to distinguish the abiotic rate from the biological rate. Detectability of oxygen on this planet, life detectability using oxygen on this planet drops by a factor of 100 because the biological rate and the non-biological rate are of the same order, and the detectability index is now 1. More water is going to make this system even worse. We know there are planets with weight percent water, like the TRAPPIST system planets. That much water is going to yield a high pressure ice mantle, we think. And so now the bottom of this ocean has an ice mantle. This is going to severely, like almost completely curtail weathering on these continents, and may even completely reduce water-rock reactions at the seafloor. Now it's extremely difficult to supply phosphorus to the planet, and we estimate that the biological production rate is now actually smaller than the production rate by photolysis, and the detectability index is now less than 1. On a planet like this, oxygen might be a very poor biosignature. So what have we learned? Any one of these planets could have oxygen in their atmosphere, but we need to know something about their non-biological geochemical cycles to assess whether it's plausible that the oxygen is produced by life. So let's look at what I showed you. Earth, with 1 ocean of water, has a detectability index of 3 because biology produces orders of magnitude more oxygen than photolysis of water. Therefore, oxygen has the potential to be a very useful biosignature. On a pelagic planet with 5 oceans of water, phosphorus is limited because there's not so much weathering of continents, and the oxygen detectability index we calculate is only 1. On this planet, it is very difficult to say whether the oxygen produced in that atmosphere is due to life or due to photolysis of water. On a water world with 40 oceans of water, we calculate a detectability index that's less than 1, possibly much less than 1. And in this case, oxygen is a very poor biosignature because the oxygen present in the atmosphere is most likely due to photolysis. So the detectability index can help us to prioritize those planets for which oxygen might be a good biosignature. So to sum up, we know almost nothing about phosphorus in stars and planets, and we're going to need to predict phosphorus and nitrogen in planets from their stellar compositions. We're going to need more data for stellar compositions. I also told you that too much water may be a problem for life detectability. Our detectability index is a first step at quantifying plausible biological and non-biological rates. And we use this detectability index, which suggests that biological rates may be equivalent to or even lower than non-biological rates on water worlds, planets with substantially more water than the Earth. So thank you for your attention. I'm very happy to take questions. You can either email me or send me a tweet. I am @AZOceanographer, or you can participate in the question and answer session.